Okay, so here we go with matrices again. And so we're doing determinants and inverses. So multiplicative identity. So the multiplicative identity is a matrix that has ones on the main diagonal and zeros everywhere else. Identity matrices are all square matrices, 2 by 2, 3 by 3, 4 by 4, etc. And they have ones on the diagonals and 2 everywhere else. A 2 by 2 matrix, 1, 0, 0, 1. That's what they look like. Ones on the diagonals, 0 everywhere else, and they're always square. Oh, I forgot. Here are 2 examples of them. Okay. So there's a 2 by 2 and a 3 by 3. Suppose A is an n by n matrix. So if I have an n by n matrix, if there exists an n by n matrix A inverse, such that A inverse times A and A times A inverse is equal to the identity matrix. So if A, then A inverse is a multiplicative inverse. If there exists a matrix such that when I multiply it times A, and I multiply A times another one, because remember, it's not the same in both directions. A times B does not equal B times A with matrices. Okay, it needs to be a square matrix. If I have a square matrix that I multiply it times another square matrix and I get the identity, those 2 matrices are multiplicative inverses of each other. Clear as mud, right? Okay, so show that the following ones are multiplicative inverses. So here's what you do. You multiply A times B. And hang on a second, here we go. Got to do this again. Because, man, this sucker's dying on me. Okay, so A times B means that I take matrix A, 1, 2, 3, 5, times matrix B, 5, 2, 3, 1, and I multiply them together. So I do this row times this column to get the first one. Negative 1 times 5, 3 times 2, so that's negative 5 plus 6, and I do that, and I get 1 right up in the front. Then I take this row times this column to get the second one. 2 times 5, sorry, I just copied that one, that's a negative 5. 2 times 5, negative 5 times 2, and guess what? I get 0. Then I do the same thing with this column and this row to do the first spot here. Negative 1 times 3, 3 times 1, and guess what? I get 0. And then I do this row times this column. 2 times 3 is 6. And negative 5 times 1 is negative 5. And guess what? I get 1. So that one works. But remember, we have to check it in both directions. We also have to do B times A. You can't do just one direction. You must check them in both directions because they don't always equal the same thing when you multiply them out. So you have to check them both. So if I do B times A, that's 5, geez. That's 5, 2, 3, 1 times negative 1, 2, 3, negative 5. And I do this again. So I do 5 times 3, 5 and 3 times 1 and 2. So 5, negative 1, 6. And lo and behold, I get 1 in the top. And then I do the same thing here. I do 2 times 1 times negative 1 and 2. And I get 0 again. 5 times 3 and negative 5, and I get 0. 2 and 1 times 3 and 5, and I get 1 again. Check, so they are inverse matrices. So now I need to do this again with G and H. So I do G times H. And I do all the corresponding ones here times all the corresponding ones there and add them together. So for, it's not going to be that big. There's going to be much bigger than that. So G times H. So I do this row times this column, which basically means, what do? I take all of these ones in this first one times -1, change their signs and add them together. So I get -15, +12, and +4, add all those together, and lo and behold, I get 1. And then I do the same thing. Then I take this one times this one. So I do 4, 5, and 0 times those. So I do 4 times 15 and 5 times 12. Well, 4 times 15 is 16. 5 times 12 is 60. So I get negative there, and then 0 times that, I get 0. And then I do this one here, 0 times these. So 0 times 15, 1 times -3 times -12, and -3 times 4, and I get 0 again. And then I repeat with this column. So I take all of these, change their signs, and add them together. -4, 3, 1, I get 0. Oh, that's so nice and easy that way. Then I do the same thing, 4 and 5 and 0 times these. 4 times 4 is 16. 5 times -3 is -15. That's 1. Plus 0 gives me 1. And then I do 0, 1, and 3 times 4, -3, and -3. So I get 0, -3, +3, add them together, I get 0. And then I do the same thing for the last column. -1 times all of these and add them together. +5, -4, -1, I get 0. 4, 5, and 0, -20, +20 and 0, that gives me 0. 1, -1, 0, 1, -3, 0, 1, -3 times those, so I get 0. And 4 and -3, that gives me 1. And hey, it worked for that. And then once again, you have to do H times G. And you guys can't see it right now, but I'm doing all these cool slow motion moves, bending over backwards, writing this upside down. You would not believe what I am doing here. Imagine me in this big black trench coat, just moving like awesomely crazy. Look, I'm going to do this next one writing upside down. So I do this. I do H times G, which means I'm doing the exact opposite. I am doing these rows times these columns. So 15, 4, and -5 times -1, 4, and 0. So I get 15, 20, sorry, 15 times -1, 4 times 4, that's 16, and then -5 times 0, so I get -15 and 16, that gives me 1. And then I take this row times this column, and I do it all over again, and I end up getting 0. Yeah. Right? Let's see. Got to make sure I'm doing it right. So I do first column, so second row, first column, second row, first column, -12, so that's 12. Yeah, I'm throwing off because I'm looking at the second one here. Okay, then I do the same thing with this one here, and I'll get 0 again. And, you know, I'm going to save us all the time and effort because, man, it is really hard standing upside down and trying to write this all at the same time. But I'm going to save us all a little bit of time here and say, yes, it does work out. Okay, now I'm back on my feet again. I'm back to normal, not doing this stupid thing here. Look, the big black trench coat's gone and everything. Ugh. Okay, so that's how you do multiplicative inverses. And yes, you do have to do them both ways. If this was a test question and you only gave me half of it, you would only get half credit. So determinant and inverse of a 2x2 matrix. Okay, the determinant of a 2x2 matrix. You multiply the two diagonals and subtract them from each other. A times D minus C times B. That is the determinant of a matrix. You can only do determinants of square matrices. And you use that determinant to find the inverse. So in order to find the inverse, you find the determinant. The inverse of a matrix is you do 1 over the determinant times, and then you rearrange and change the signs. So you take the A and the D and you swap them. The C and the B same in the same place, but you change their signs and you multiply that times 1 over the determinant, and that will give you your inverse matrix. So Let's find the determinants and inverse matrices of these ones here. So the determinant is you multiply the 2 across, 2 times 3, minus multiply across the other way, 5 times 1, so I get 6 minus 1, so my determinant is 1. Oh, that's really, really, really easy to find the inverse matrix. So A inverse is equal to 1 over the determinant, which is 1 over 1, times, I swap the diagonals across this way, A and D, so I get 3 here and 2 here, and then I change the sign of the other ones just to change their signs. That's what I have to do. Then I multiply times that, and I get A inverse is equal to 3, negative 5, negative 1, 2. That's how you find the inverse of a 2 by 2 matrix. So I want to find the multiplicative inverse of B. First thing I need to do is I need to find the determinant. So I multiply these two, I get negative 4 minus, multiply these two, which is negative 6. Negative 4 minus negative 6 is 2. So my determinant is 2. B inverse is equal to 1 over the determinant, 1/2, times the 2 by 2 where I swap the first diagonals, A and D, so I get 4 and negative 1. Then I change the signs of the other ones, so I get negative 3 and positive 2, and I multiply all of those, in this case, by 1/2. So B inverse is equal to 2, negative 3/2, 1, and negative 1/2. And that is the multiplicative inverse. And then the last one here, our determinant, is multiply these two, 10 times 1 is 10, minus multiply these two, negative 5 times 2 is 10, and I get 0. My determinant is 0, so there is no multiplicative inverse. Because what do I need to multiply? To find the inverse of C, my first step is to do 1 over the determinant, which would give me 1 times 1 over 0. That would be undefined. It does not exist. Okay. Moving on. Solve the system's equations in 2 variables using inverse matrices. So if I have the matrix set up where I have A, X, and B, those are matrices. A, and in this case I'm doing it with 2 by 2s, but you can do this with any system of equations. A is the coefficients. So in this case, my first one, my A matrix would be 5, 6, negative 4, negative 5. And then X is the variables, X and Y. And then B is what the whole thing is equal to. And I'm going to write B over here. Okay, I'm going to make B over here, and you'll see why in a minute. I'm going to put 2 over 1. So if you look at this closely, what it is that, hey, this is what I have down here. A, X, and B. If I take the inverse of A and multiply it times AX, take the inverse of A times B, if I multiply both sides by the inverse of A, what happens? The A inverse times A inverse becomes the identity, so that means that gives me just X equals the inverse of A times B. That means I get my answer. I get my variables. So the first thing I need to do is I need to find A inverse. So I have A here. I need to find A inverse. So the determinant, I have to do that one first. My determinant is 5 times negative 5, negative 25, minus 6 times negative 4, which is negative 24. Right, so what do I get? I end up getting negative 1 as my determinant. Oh, that's really, really nice. Makes it easy to find my inverse matrix. Because what do? That means I take to find A inverse, I take 1 over the determinant, 1 over negative 1, which is negative 1, times I take A and I swap the 2 diagonals, negative 5 and 5, and then I change the sign of the other 2 numbers, so I get negative 6 and positive 4. And then when I get my inverse, I just multiply all of these times -1, and that will give me A inverse as 5, 6, -4, -5. And if I multiply this times A inverse and this times A inverse, I end up getting X, which is XY, equaling, and I multiply these two together, and that will give me my answer. So I take this row times this column. So I do 5 minus 4 times 2 and 1. So I end up with 10 minus 4. I get 6. And then I do this one times this one here. 6 negative 5 times 2 and 1. 6 times 2 is 12. Minus 5 is 7. So that means my solution to this, x equals 6, y equals 7. Using matrices to solve a system of equations. Is it really the best way to solve a 2x2? No, it's not the best way to solve a 2x2, but it does work. We will use it for larger things later. Ooh, previews. Okay. So, let's do this again. Notice there's a problem. First thing I have to do is I have to make them so it's an actual system that I can solve properly, which means I need to rearrange this bottom equation. 2x minus 3y equals 1. Everything has to line up. Okay? So then I get my a, my x, and my b accordingly. So my a is the coefficients 4, 2, -7, -3. X is the variables x, y. And then b would be my solutions, -3 and 1. Okay, so I have a, x, x, and b. And to find my answer, I need to find a inverse and multiply it times b. So to find a inverse, first I need to find the determinant. My determinant, multiply across, -12, multiply across, minus -14. My determinant ends up being 2. So that means that a inverse is 1/2 times, and I swap the diagonals on the first one, so I swap a and d, so I get -3, and I have 4, and then I change the sign of the other two, I get -2 and +7. And I multiply that out to get a inverse. I get -3/2 and 1 and 7/2 and 2. And then to find my solution, to figure out what x is, I need to take this, a inverse, times this, which is b. So I have -3/2 and 1 and 7/2 and 2 times -3, 1. And what do I get from doing that? Multiply across, multiply down. -3 times -3/2 is -9/2. 1 times 7/2. -9/2 plus 7/2 gives me -2/2, which is -2/2 is -1. Right? Did I do that one right? I screwed something up. Where did I screw up? Oh, that's plus. Duh, no wonder. My bad. And then so it's negative, it's +9/2, 7/2, that's 16/2, which is 8. Okay, I screwed that one up. Now I do this row, 1, 2 times -3, 1, and add them together. So basically it's -3 plus 4 gives me should be a -1. Yeah, that should be -1. That's a -1. That's my bad. So I'm getting 3 plus 6, or sorry, 3 plus 2, and I get 5. So that means that x equals 8 and y equals 5. Okay. Questions? Too bad. You're not here to ask them anyways. Hey, use matrices to encode and decode the word math. Matrices is another way of doing Code work. Okay, secret codes. So the first thing you need to do is code the word math. Well, how can we do that? How can we make math numerically? What you do is you assign each of the letters a number. This is 13, that's 1, that is 20, and this one is 8. So I can make this into the matrix. 13, 1, 20, and 8. Makes it nice. To encode it, you multiply it by an invertible matrix. So you multiply it times an invertible matrix. So you have to have a matrix that does have an inverse. You've got to find one, you've got to do the inverse. It doesn't matter, you can pick one, you can make one up. I'm going to use a perfect example here, the one that works. So I take that times an invertible matrix. So if I call that, that's the one I have, I need to do the invertible matrix first. So I do A inverse times A. I do that first. Or I should say A times, let's call this M for math. I'm going to call this, actually I'll call this one A, and my invertible matrix I will call B. So I do B times A. So I take my invertible matrix times my math one. So I'm going to pick my invertible matrix as -2, -3, 3, 4. It's one that works out really nice, actually. And I multiply that times the inverse for what I'm trying to encode. 13, 1, 20, and 8. And when you multiply those two together, you get -29, 43, -64, and 92. And this is our encoded. We have created our secret code. Our secret code is multiplying it times this. Now to decode, you find the inverse. Of your invertible matrix. So you find the inverse of your invertible matrix. So my invertible matrix was this. You go and you find its inverse. The inverse of that one ends up, because what's my D on this one? It ends up being -8 minus -9, which is 1. So it's 1 times you swap them and change the sign. So that would be 4, -3, 3, and -2. And you multiply it times our encoded matrix, -29, 43, -64, and 92. And you multiply those two together. And look what we get. We got our original ones out. We get M, A, T, H. Bingo, we're done.